In this lesson, we're going to talk about what's called a magnetic bottle or magnetic confinement of charged particles. Now, the specific details, as we sneak down here and look at our magnetic bottle, which I'll get to in a moment, you will not need to know either for our tests or for the AP tests. It's kind of FYI. This type of magnetic confinement is used when charged particles carry so much energy that you can't confine them in a conventional bottle. They would melt the bottle. They're so hot. They have so much energy. So that's why it's called a magnetic bottle, a magnetic confinement, because we actually use the magnetic field as a way of trapping the particles and holding the particles in the same way a regular container or pitcher holds water. So what do we have here? In terms of what you do need to understand for our course and for the AP test would be the notion of magnetic fields allowing particles to spiral around them in this helical sense. So I'm going to zoom in here. So if a charged particle, here a positively charged particle, is injected just at some random angle to the B field. So my positively charged particle, if it's injected at some random angle, in general, it will have a perpendicular component to the magnetic field and a parallel component. Now, the perpendicular component we've looked at before, and I would like you to put in here just our circular motion. FB equals QV cross B equals MV squared on R. And that always makes circular motion. And please add to your notes to see page 7 of notes. So the V perpendicular and our red equation here is all the same as page 7 of the notes. So I want to go back very quickly. 9, 8, 7. And that is what we had here. So when you have the particle, so we have our positively charged particle injected into the magnetic field, where the magnetic field is, in this case, into the page, V is in the plane of the page, it is only V perpendicular. There is no V parallel. So the charged particle is not spiraling into the page or isn't spiraling out of the page because we didn't add a velocity into the page or out of the page in this example. We simply did QV cross B, where we had 90 degrees between them. That equaled mv squared on r, and we got our circular motion in the plane of the page. So this is what we have already been looking at, and that is the V perpendicular only. All right, if we add the velocity into the page or out of the page, that's our V parallel. So that's where the magnetic force doesn't do anything to that V into the page or out of the page, or in this case what I have shown here as the V parallel, where that V stays in place and the circular motion occurs and the translation occurs. So you get both, and in general, charged particles spiral in helical paths around magnetic fields, and that is by far the most important thing off of this page of notes. That you know that that's the general motion of a charged particle in relationship to magnetic fields. They spiral, charged particles spiral around magnetic fields. Okay, now for the FYI part, the magnetic bottle. Well, first of all, a magnetic bottle is very easy to make because if we take a bar magnet, refrigerator magnet, you can put the North Pole here. You can put the South Pole here. They want to pull together, but if you hold them apart from pulling together, you have made a magnetic bottle. So the magnetic field lines come out of north, go into south, and we get a non-uniform magnetic field because as we pull them apart, you have a weaker B field in the middle. So what you get is the spiraling, right? So we get the spiraling that we just talked about. I'll zoom in here. So we get the spiraling as the particle spirals to the right, but the radius is now going to increase. And as the non-uniform B field, right, comes into play, all of the instantaneous velocity vectors that go with the B field, that go with the velocity vector, that go with the magnetic force are based on tangents to the field lines. So that is why they are showing you the V vector and the B vector. The B vector, if I can draw it in here, the B vector, if this is the magnetic field itself, so this is, if that's the B vector, at this instant in time, it's tangent. So if I have my V vector here, I get my force is actually kind of on this little diagonal here. But keep in mind, magnetic forces never speed particles up. The deflection is now just angled. So it's angled a little bit to the right in this perspective. Now, what I'm not going to go into detail with you about, but as the spiraling occurs, right, so as it spirals along, keeps going to the right, at some point, it will now actually reverse direction, because the same description we had for the magnetic force now begins to point to the left. And at some point, and please add this, because it's not an oscillation that stops. The particle never stops moving because the magnetic field never changes the speed of the particle. So it keeps going, but at some point, it is now going to travel back on itself and reverse direction. So it never actually stops. So put that in here. Never actually stops. And that's kind of what I have down here. The force will change V parallel from going from the right to the left, but V perpendicular must also change so that the magnitude does not change. So the V does not change. And the fact that the force changes direction, we've seen before. So in terms of the force changing direction and the velocity changing direction, the particle not changing speed, is what I have shown down here for basic circular motion in the plane of the page. If we consider, let me go back here. If we consider the velocity vector tangent to the right down here, the magnetic force is up, the B field is into the paper. Do QV cross B, your thumb is up if this is a positively charged particle. Well, that continues until you get to the top, where now look, it's reversed direction. It's now going to the left. So the particle was going to the right down here. It's going to the left up here. It hasn't changed direction. And the magnetic force has changed direction now to down, but still radially in. That same type of movement is what's occurring in the magnetic bottle, but you have the translation that goes along with it, so it's just much harder to visualize. But I hope you just get a flavor for what is going on with the magnetic bottle and can see that it is possible. Whether you see all the details, you do not need to know it for this course or for, like I say, our tests. But the fact that charged particles spiral around magnetic fields, yes, that you do need to know. So that is all I have for this page of notes. Magnetic confinement in magnetic bottles is used for fusion type experiments or any experiments where you have high energy charged particles that you want to contain but simply can't contain them in a conventional bottle because the bottle would melt.